Welcome to this lecture on studying the role of determinants in solving linear system of equations. So, the topic that we are going to talk about today is solving linear system of equations. So, over the past 3 lectures we have looked at different aspects of determinants, starting from where they may arise. So, one of the motivating examples was in fact solving system of equations, linear system of equations. Then we also saw how they have a geometrical interpretation, then we defined a determinant. So, that was all in the first lecture. In the next lecture we looked at some of the properties which will help in efficiently calculating determinant values. Then we saw one application of determinants. We saw how determinants can be helpful in calculating inverses of square matrices, giving conditions whether a matrix will have an inverse or not. And in that line today we will look at how they help in solving linear system of equations. So, the idea is again straightforward, and it is one of generalizing simple equations that we usually see. So, we may see equations like 2x equal to 3 and we want to solve for the variable x. Similarly, we have more than one equation in suppose we have equations which have multiple unknowns x and y or x, y and z, in general n equations, then we have seen how we can convert these representations into a matrix representation. So, we can write down a general equation A x equal to b, where A is a general n by n square matrix typically if there are n unknowns and n equations, and then we would like to solve it. So, here we are going to look at how we can use determinants to address this issue, and what we will see is how the determinants or calculating the determinants of the associated matrix will give a condition to find out whether there is a solution or no solutions or many solutions, right. So, that is what our goal is. So, just to write that down, we may have previously encountered equations like A x equal to b, where A may be some scalar, b also is a scalar, and x is an unknown that needs to be solved for, and because these are all scalar values, we can say okay, if A is not equal to 0, then x equal to b by a, right. Now, when we generalize these to have, let us say, equation in two unknowns A x plus b y equal to m and c x plus d y equal to n, where now x and y are unknowns. So, there are two unknowns and two equations. How will we find the solutions of this? And we know that we can write this down in a matrix representation A, B, C, D, and there is x, y, and then m and n, right. So, this plays the role of an A matrix. This is an unknown vector. So, to avoid confusing the notation, let us say this is a vector x, right, with the underbar. So, this x is a scalar, this is a vector. So, let me just make a note of that. This is a vector, right, 2 dimensional in this case, and these are also known constants. Now, A is known and this thing on the right hand side of the equation is also known, but x is unknown. So, this representation of A times x equal to a known value, let us call that capital B is equal to B. So, how can we get the value of x over here? So, it is the same generalization of what we see in one dimensional, this is in 2 dimension, and in general we can have a situation in n dimensions. So, how do we solve these system of equations, these linear system of equations? what is the role of determinants in this. That is the goal of this lecture. All right. So, how do we use determinants, how do we solve these equations, how do we come up with conditions to check their existence of solutions or not. So, we will look at the associated concepts and also look at some problems over here. Okay. So, just to carry on with the previous example, we have something like A, B, C, D times x, y equal to m and n. So, we have said this is A, this is an unknown vector x, this is B. Okay. Now, the goal, as we just said, is to find out how to solve for x, right. And so, just a point about notation that we are going to use. Once the context is clear, we are going to say we are going to replace x with just ordinary notation x, not to be confused by the scalar x. So, in appropriate context, we use x to denote the vector value, right. Although we will try to be careful to use the x with the underbar to avoid any confusion. Okay. So, now we have, this is an example of a two dimensional system, that is that there are two unknowns and there are two equations. Just for the sake of completeness, let us write down a three dimensional system of equations and then define the associated quantities. 3 by 3 example, a 3 dimensional example, 3 dimensional example. Okay. So, here we say there are 3 equations, a11x plus a12y plus a13z equal to b1. Okay. This is equation 1. The second equation may be a21x plus a22y plus a23z equal to b2, and the third equation is a31x plus a32y plus a33z equal to b3. So, this is an example of 3 equations with 3 unknowns x, y and z, each of which are scalars. So, how do we write down this in the general matrix representation? Well, we can collect the terms like we have done for a 2 dimensional system into a square matrix A. We are going to call it A, we are going to call it capital A, and then an unknown vector x with the underbar, which is a column vector having the unknown values x, y and z, and then on the right hand side of the equation will be another column vector with the entries b1, b2, b3, which you should call capital B. So, we can write this down as a matrix a11, a12, a13, a21, a22, a23, a31, a32, a33, and then a column vector here x, y, z, and then vector b1, b2, b3. So, this may be denoted as capital A, this is x bar, and this is capital B. So, the equation that we have is A times x bar is equal to B, and our goal over here is to find x. So, the purpose of writing down the 3 dimensional system of equation was to show, when you compare it with a 2 dimensional system, that in general you can write this down for an n dimensional system which has n equations and n unknowns. So, here is just a case for n equal to 3. We can in general take A, x bar and B to be their appropriate n dimensional quantities. Specifically, A is going to be an n by n square matrix, x is going to be a n by 1 vector, and B is going to be a n by 1 vector. So, in general, this is a n by n square matrix, this is a n by 1 vector, and so is this an n by 1 vector. So, this is the problem setup, Ax equal to B, a linear system of equations. How do we look for solutions? How do we check for conditions for which this has solutions or not? So, the general system is the following: Ax equal to B. Now, here I want to take this opportunity to define two terms which are frequently used in this context. They are opposites of each other. So, one of the terms is consistent. So, a system of equations is said to be consistent if it has a solution. So, it could be one or more solutions, and it is said to be inconsistent if there are no solutions. So, let me write these down, but these are terms which are defined given this context of having a system of equations and trying to solve for these unknown values. Consistency, a system of equations such as the one shown here is said to be consistent if a solution exists and of course, there may be one solution or more than one solution. And the analogous definition of inconsistency is a system of equations is said to be inconsistent if a solution does not exist. So, let us look at these again. So, these are the system of equations referred to here, system of equations. A system of equations is said to be consistent if a solution exists, meaning that x has one solution or more than one solution. Inconsistency, a system of equations is said to be inconsistent if a solution does not exist, meaning that there is no x which satisfies these for the given values of the matrices A and B. Okay. So, the goal of saying these terms consistency and inconsistency is to give a short form expression for saying or for handling or talking about solutions of x. So, we will say system of equations is consistent or system of equations is inconsistent, and that would mean short form for saying whether it has a solution or does not have a solution. On that note, I must mention that a lot of interchangeable terms are used. So, for example, if a system of equations has just one solution, we say it has a unique solution, unique meaning one solution. Sometimes they talk about a non-trivial solution, non-trivial meaning that the solution that you get x is not equal to 0. So, these are some other terms which are used in the context. For our purposes, we will keep it simple and just use consistency and inconsistency. Okay. So, how do we go about solving this? So, A x equal to b. We want to know what is the consistency properties, what is the inconsistency, is it consistent, inconsistent, how to check. Right? This is what we set out to find, how to check whether system of equations are consistent or not. And this is where now we talk about the role of determinants, especially in deciding whether the matrix A is invertible or not. So, our program is as follows. We will say, okay, as we have seen in the previous lecture, a matrix can be singular or non-singular depending on whether its determinant is 0 or not. If it is non-singular, that is if the determinant is 0, then it is invertible, and if it is invertible, then we have a matrix inverse which we call A inverse, which we can multiply these equations by. And in that case, when we multiply the equation by A inverse, the left hand side will become A inverse times A times x, and the right hand side will become A inverse times b. And if A inverse times A, we know by definition is identity, then we have a ready made solution for x. Then we look at the other case when it is not invertible and then see what happens over there. So, let us write down what we just said. So, if the first case that we will look at is that A is non-singular. What does that mean? That means that the determinant of A is not equal to 0. The immediate implication is A inverse exists. Okay. So, if A inverse exists, let us multiply both sides of this equation by A inverse. What do we get? We get that A inverse A x bar is equal to A inverse times B. This we know is identity. So, if it is a 2-dimensional matrix A, then this is a 2-dimensional identity which is 1 0 0 1. In general, if it is an n-dimensional matrix A, it is an n-dimensional identity. So, it has n rows, n columns, and all the diagonal entries are 1. So, identity times x is x. So, this we get x is A inverse times B. So, in the case that A is non singular, the solution that we get is x is equal to A inverse B. Right. So, this is the first case in which it is non singular, that is the determinant is non-zero. So, we have a ready made solution for this. Okay. Now, what about the other case? Well, there we again use the tools that we developed in defining the matrix inverse, specifically the adjoint matrix. So, in the case that determinant is 0, then we can easily see that the adjoint of A times A is 0, right, because previously we had come up with this relation that adjoint of A times capital A is equal to the identity times the determinant of A. And so, if determinant is 0, it means that the adjoint of A times A is 0. Then let us see what happens. So, the second case is if A is singular, that is determinant of A is 0. So, we had seen that adjoint of A times A is a determinant of A times identity, which because this is 0, this is equal to 0 matrix. And so, we use this by multiplying the system of equations by the adjoint of A. So, if you multiply this, then we get that adjoint of A times x bar is equal to adjoint of A times B. So, I am missing a A here. So, this should be adjoint of A times x bar, right. So, that makes sense because the left hand side has A x bar. So, we have adjoint of A times A x bar and then adjoint of A times B. Now, from here we know that this term is 0. So, the left hand side is 0 and then we have adjoint of A times B, right. So, now there are two cases. The sub case A, small a, is if adjoint of A times B is equal to 0, then we cannot say anything. So, then we cannot say anything about consistency or inconsistency, consistency or inconsistency. So, it is a inconclusive result. In case that the adjoint of A, so this is the case 2b, if the adjoint of A times B is not equal to 0, then we have a problem, because the right hand side is not 0, the left hand side is 0. So, in this case it is, we say that the system is inconsistent. Right. So, here there are questions about how well posed this is, because the left hand side is 0, right hand side is not 0, how can we equate the two, right. So, in this case when A is singular, most of the conclusions that we can come up with are the following. The modus of operation is that we say, okay, we are going to multiply by the adjoint of A, just like we did with the A inverse in the previous case. Of course, previously it was a much simpler situation, because we knew that A inverse exists, it is A inverse times A is identity, and so we could get a ready made solution for x. Here it is a little bit more complicated, because here we do not know what the inverse is. In fact, we know that it does not exist. So, we cannot do what we did previously. So, what we do here is that we multiply by the adjoint, and then in the case that the adjoint of A times a B matrix, the constant matrix on the right hand side of the equation, depending on whether it is 0 or not 0, then we have the conclusion that we have just written down. Okay. So, this is overall how we use the idea of determinants, and in particular its role in determining the matrix inverses to address the issues about consistency and inconsistency in a linear system of equations. So far we have talked about we have motivated using 2-dimensional or 3-dimensional examples, and now we have motivated the problem and then said, okay, let us consider a general n by n square matrix which is about n equations and n unknowns, and then we have come up with a general way to address the issue of whether it has a solution or it has a no solution. And so, this is sort of the conceptual understanding behind what we want to look at in terms of solving systems of equation. Next, let us look at some examples and try to explore or interpret these issues through these examples. Okay. So, the first example which I want to present is something which we have looked at previously. Let us continue in this algebraic vein to see what results we get. So, this system of equations that we had written in the first lecture had as the matrix A 1 1 4 minus 1 times x y, and this was equal to 10 0. So, this plays the role of A, this plays the role of x bar, and this plays the role of the B matrix. All right. So, these are to put just some numbers in these values, just to get an idea about how do we actually go about the issue. So, the first thing that we did is to check whether there are solutions or not, and so for this what we will do is that we will look at the determinant of A. It is a 2 by 2 matrix, determinant should be relatively easy. Let us see if we can figure it out. So, the determinant of A here is equal to 2 by 2 matrix, so we can either do 1 minus 1, so minus 1 minus 4 to minus 5, or we could do using the definition, which boils down to nothing but the same expression. So, we are multiplying 1 minus 1, so that is minus 1, that is why this term comes, and then over here you have minus 4 times 1, so minus 4 is minus 5, and the important thing to note is that it is not equal to 0, and so this is the first case that we apply. And what this tells us is, okay, this system of equations has a solution. In fact, when we explore the use of the inverse in trying to find the solution, we see that we can also construct the solution. So, the solution, so this says that this has a solution, this implies that this has a solution. How to find the solution? What is the solution? The solution of x is A inverse times B, right. So, using the fact that determinant is not 0, we can say that this is a consistent system of equation. What is the solution? There we have this x bar is A inverse times B. So, what is A inverse? A inverse in this case is minus 1 by 5 times replacing the matrix A with its adjoint. So, minus 1, 1, minus 1, minus 4. So, I believe this is the inverse of the matrix. We can also check by multiplying this equation with this, and it does turn out that it looks to be the identity, alright. So, this is the inverse, and so the solution, so what is A inverse times B? This is minus 1 by 5. Let me just write down A inverse again, minus 1, minus 1, minus 4, 1, and then 10, 0. So, implies that x bar is minus 1 by 5 minus 1, so that is minus 10 and minus 4 minus 40. So, this is 2 and 8. So, this is the solution, right. So, what we have done here is the following. First, we have checked whether this system of equations has a solution or not, and in doing that we first calculate the determinant. Determinant is not 0, so it is a non-singular matrix, therefore, it is a consistent system of equations, and then we say, okay, if it is consistent, what is the solution, and this is in the construction of the solution. In previously we have seen that the solution is A inverse times B, and so we calculate A inverse, multiply it by B, and then we get the solution. Now, we can of course check whether this solution of 2, 8 satisfies the two individual equations. So, let us check that. So, let us verify whether x bar equal to 2 comma 2, 8 satisfies the equations or not. So, what are the equations? So, now let us write them down in their original algebraic forms, where you have 2 equations in 2 unknowns, so 4x minus y, right. So, suppose we put x equal to 2 and y equal to 8, then yes, we see that x plus y equal to 10, because 2 plus 8 is 10. Suppose we put this here, so x is 2, so 4 into 2 is 8, minus 8 is 0. So, therefore, this solution satisfies the original equations. Right. So, this is just a sanity check, if you will, that we have come up with a new, for some of us, way to find out the solution, and we see that if you get the solution, then by the direct substitution techniques we can come up with checking, or a way to check whether the solution satisfies the equations, and yes, we find that the solution is proper solution of these equations. Okay. So far we have looked at this issue algebraically, and especially because this is a two dimensional example and it is easy to visualize the geometric aspect of this issue, we are going to look at that. In particular, we are going to interpret these results from a geometric point of view, and just to get an alternative understanding, a geometrical layer to this issue of consistency or inconsistency of system of equations. So, we will look at the same example, but from a geometric point of view. So, the geometry of this example. So, these are two equations. So, these were x plus y is equal to 10 and 4x minus y equal to 0. Now, looking at these two equations from a geometric point of view, these are lines, these are equations of lines in a coordinate frame. So, let me draw it down. So, this is a coordinate frame. Let us say this is the x axis, this is the y axis. X plus y equal to 10 is a line like this, which has as points here 10 0 and 0 10. It is a rough sketch, but the idea here is to get the general shape of these lines proper. 4x minus y equal to 0 is a line like that. So, this is 4x minus y equal to 0 and this is x plus y is equal to 10. And what are we trying to do when we are trying to find a solution for this? We are trying to find a set of values small x, small y, which will satisfy both these equations. So, from a geometric point of view, what we are trying to see is whether these two lines intersect at a point or not. Why is that? Because if they intersect at a point, then that point is going to satisfy the equation of both the lines. So, this point should satisfy both this equation and also this equation. And based on the previous analysis of the example, we say that this is the point 2, 8, and we have seen that it lies both on this line and also on this line. So, the point of intersection satisfies the equation of both the lines, and that is the solution that we are looking for, right. So, this is a consistent system of equations. Let us see. So, continuing from this idea that okay, we can geometrically visualize these two lines as follows. In what cases what two lines will have no solution, in the sense that what two lines will have no points of intersection? Well, one possibility is that if the two lines are parallel to each other, then by definition they do not intersect, and so that may be a situation where the solution is going to be inconsistent, that is, the system of equations is going to have no solution and it will be labeled as inconsistent. So, let us see based on this example whether we can come up with a system of equations which have no solution. So, suppose we have in mind that we are going to construct a inconsistent system. So, suppose we look at again in the phase plane two lines. So, this as original is x plus y equal to 10. Suppose we have another system, another line which is x plus y equal to 20. This is x, this is y, and clearly these are two parallel lines. So, if we write down these equations like x plus y equal to 10, x plus y equal to 20, and we try to come up with a matrix version of these two equations and check in our previous way whether this is going to have a solution or not. based on our understanding of the geometry, because these are parallel lines, there should be no point of intersection, and so there should be no solution. But let us just check, the idea being that okay, we know what is happening, but let us check the established procedure that we are trying to look into to see whether there is two match. So, what we would do then is that we say okay, this is something like 1 1 1 1 x y and 10 20, and we want to know whether this system is singular or not. So, first calculate the determinant is 0, and we then say okay, determinant of A is 1 minus 1, so that is 0. So, clearly we cannot construct a solution like before in terms of A inverse times B. As we are seeing, let us see what happens when we look at the adjoint of A. What is the adjoint of A? Adjoint of A is replacing 1 1 minus 1 minus 1. So, this is the adjoint of A, because the cofactor of 1 is 1. So, that is put here, cofactor of this one is minus 1, and that is put here. Of course, these are the same entries, so it is a symmetric matrix, but in general it need not be. So, then we will check whether what is the value of adjoint of A times B. So, in this case this is B. So, what is adjoint of A times B? This is 1 minus 1 minus 1 1 times 10 20, and this is going to be 10 minus 20, so minus 10 and then plus 10. So, we have a situation where the right hand side of the equation, which we obtained by multiplying adjoint of A times A x bar equal to B, the right hand side is non-zero, but the left hand side, because adjoint of A times A is 0. So, we know that we can check directly here, that is 0. So, this will come up with a situation where 0 is equal to something which is not 0. So, this does not make sense, and that is why we labeled it inconsistent. And from a geometric point of view, we can see that these are two parallel lines, so there should not be any solution, and that also is along the lines of our idea of a consistent system of equations. So, the goal of this exercise here was to say okay, from a purely algebraic matrix point of view, perhaps it is not so clear why is it the case that we label these as inconsistent. Here we can look at it geometrically and say okay, parallel lines, no point of intersection, no solution, therefore, by definition they are inconsistent. Okay. So, here is an example where there is no solution. Now, remember in the idea of defining something as consistent, we had said there could be one solution or more than one solution, and we have looked at an example where there is one solution. Can we think of an example where there may be more than one solution, and particularly in infinite number of solutions? Well, going back to this geometrical idea of saying that these are lines in a plane, let us consider what happens when the two lines describe the same equation. If you have two lines which describe the same equation, or I apologize if I say, I should have said if the two equations describe the same line, then what happens? Then two lines are on top of each other. So, any point x and y which is on the line is going to solve the system of equations. So, that is what we mean when we say we have more than one solutions. From a geometrical point of view, it is that those two define the same line. So, let us just for completeness look at an example of that. We are looking at an example of possibly infinitely many solutions. So, let us geometrically, the idea is that if we have the same equation like x y, and this is an equation of the line x plus y equal to 10, if we had x plus y equal to 10 and x plus y equal to 10, it may not be directly x plus y equal to 10, it could be something like 2x plus 2y is equal to 10 into 2 or 20, because as we see this is just still the representation of the equation of the line. So, we have infinitely many solutions. Why? Because any point on this line is going to be solving these two. Just for the sake of verification, if we write this down as a system 1 1 2 2, times x y and 10 20. This is the matrix A. What is the determinant of A? There, that is also 0. So, it is not straightforward to come up with a solution. What about the adjoint of A? Like previously, we are going to write down the adjoint of A. So, what is the adjoint of 1? Adjoint of 1, the cofactor of 1, excuse me, is 2, 1 and then minus 1, minus 2. So, this is adjoint of A. What is adjoint of A times B? Adjoint of A into B is going to be 0 and 0. So, this is a case where both the left hand side and the right hand side are going to be 0. So, we cannot say anything about, so as per the procedure, we cannot conclude about consistency or inconsistency from here. So, we need something else, and so this makes sense, because from the point of view of geometrical idea, there are infinitely many solutions. So, we can use the geometry of the situation to find out whether it is consistent or not consistent. So, in these 3 cases or 3 examples, we have looked at different versions of the system of equations. In the first case, it was going to be one point of solution, and we found that it was indeed one point of solution, because that was the point of intersection of the lines. Then in the next case, we saw that these were 2 parallel lines, and so there was no solution, and that was also consistent with what we found in the system of equations being inconsistent. And finally, in this case, we come up with a case where the we cannot conclude anything about the consistency or inconsistency, and some other things may be required, and we know from the underlying geometrical picture that it is a consistent system of equations, because there are infinitely many solutions. So, let me write down this in terms of a table. So, the previous 3 sub examples, previous example, 3 variations, and the summary is as follows. In the first case, 1, determinant of A was not 0. So, then we could say what the solution is, A inverse B, and the underlying geometrical picture was one point of intersection. Second, and in particular 2A, was when the determinant was equal to 0. So, we cannot come up with that, but what we found was that this was parallel lines. So, we had found that this was actually inconsistent, and geometrically this was parallel lines. I believe this was the case 2B. Yeah, so this was the case 2B that we had looked at, corresponding to what we did in the procedure, and the case 2A was when determinant of A was 0, but we could not make a conclusion. But from the underlying geometry, we knew that this was the same line, so infinitely many solution. finitely many solutions, right. So, this is like a systematic exploration of one example to understand, especially because we can see the geometry of the situation, to understand how we go about analyzing whether a system has a solution or called consistent or inconsistent, or how we would analyze it from a general matrix point of view. So, the same procedure can be looked at in a more general situation when these are 3 by 3 or more generally n by n matrices, and here we want to highlight how just by checking the determinant of the associated matrix we can make a lot of conclusions. Next, let us look at another example of finding out whether the system of equations has solution or no solution. So, this particular example is based on a JEE problem. In particular, this is from the JEE Advanced website. www.jeeadvance.ac.in/sample questions 2016 p2.pdf. So, let me briefly illustrate what the question is. So, briefly, so and for more general, one could look up the problem in the website, which is stating the full statement. So, here we are going to consider a 2-dimensional system of equations, alpha x plus 2y equal to lambda and 3x minus 2y equal to mu, and alpha, lambda, comma mu are real numbers. So, the overall problem has many options and one has to one or more than one can be true, but let us just look at one of them and try to see whether that statement can be said to be true or not. So, one particular option, so the question is that we are going to look at is the following true, that is that if alpha is not equal to minus 3, then the system has a unique solution for all lambda and mu. Does the question make sense? So, this is based on a problem which can be accessed in this PDF file from this web page, and this is a sub part of this. So, based on problem in JEE Advanced website, and this is a part of it which we are trying to understand based on what we have done. So, we have a system of equations 2-dimensional, and we want to know that if alpha is equal to minus 3, then whether it has a unique solution or not. So, how do we find that out? Well, we can easily represent this in terms of a matrix alpha 2, 3, minus 2, and then x, y, then we have lambda, mu. So, in our notation, this is the matrix A, this is the matrix x bar, and this is B, and what we want to check is whether it has a unique solution. So, by unique we mean only one. So, first of all let us check whether it has a solution or not. How do we check that? We check that by first calculating the determinant of A. So, the determinant of A matrix is minus 2 alpha minus 6, and we note that this is determinant is not equal to 0 if alpha is not equal to minus 3, because if alpha is equal to minus 3 then this determinant is 0, therefore, if it is not equal to minus 3 it is not 0. Now, what the statement says is that okay, if determinant of A is not 0, right, because that is what they say is alpha not equal to minus 3, then what can we say about the system of equation? Then we automatically say that it is a consistent system. But does it have one solution or not for all values of lambda and mu? How do we check that? Well, let us just check it by constructing the inverse. So, the inverse is going to be minus or 1 by minus 2 alpha minus 6, and then replacing the matrix by the adjoint. So, that is minus 2 alpha 2 minus 2 minus 3 and then lambda and mu. So, what we have here is minus 1 by 2 alpha plus 6 and minus 2 minus 2. So, minus 2 lambda minus 2 mu and minus 3 lambda plus alpha mu. So, as you can see there is only one solution for a given lambda comma mu and alpha, and the alpha is given to be not equal to minus 3. So, therefore, yes, there is a unique solution, because for any value of lambda and mu we can come up with one value of this as long as alpha is not equal to minus 3. So, yes, so this statement is true. So, there are three other options given in the problem, and we can each of them can be checked using this method. So, this goal of presenting this part of this advanced problem is just to say okay, the sort of concepts and the problems and the discussion that we have been having is also something that is tested at a more advanced level, and the same tools that we have done, I mean straight away the determinant comes into picture, straight away our understanding of whether the system is consistent or not, that comes into the picture. One can also look at, and I encourage you to do so, to look at the geometrical picture of this particular problem and try to see okay, is it going to be a straight point of intersection sort of situation, or whether the lines become parallel, and so on and so forth. So, to summarize, the goal of this lecture was to investigate the role of determinants in solving system of equations, linear system of equations, and we did that for a general n by n case. We saw how constructing the system can come from simple 2 by 2 or 3 by 3 examples, and then we defined the words consistency, inconsistency, and then saw using what we learned about in the inverses matrix chapter, how the previous lecture about the matrix inverses could be used, especially the idea that the determinant determines whether it is a singular matrix or not, because that can give you an idea about whether the inverse exists or not, and then that can be used to construct the solution or to say something about whether the solution cannot be constructed. So, this again illustrates the importance of determinants in solving linear system of equations. So, let me just write that down as a summary statement. So, this lecture highlighted the role of determinants in solving linear system of equations. Okay. So, with that I thank you for your attention, and I hope the concepts and the problems that we have discussed here are of use in your understanding of the idea about determinants. Thank you.